Cool. Hi there. Very nice introduction. So, just need to check how this works. So basically, today I want to talk about the Miden VM, which was basically built by Bobbin and many others, at least the mastermind behind that. And basically, the thesis of this talk is that Turing-complete zero-knowledge virtual machines can enable developers to use this cool technology without needing to have a PhD in math. There are different types of ZK-VMs for different use cases, and the Miden VM is for client-side proofs and blockchains. We will dive into the design of the Miden VM, into the technical design, depends, like we can see how deep we can go there, and how a Miden program looks like, and then we prove something together. So let's dive into it. Maybe I go a bit here. Basically, the Miden VM is a virtual machine, and for most of you it might be repetitive, but like a virtual machine basically is some kind of program where you put in an initial state and the program, and you get a final state out. And the difference to a zero-knowledge virtual machine is just that now we get a final state out, but also a proof. Right? And the cool thing is that we can also add a witness or like a secret input. So we have a public input into our virtual machine and a secret input. And the cool thing about the secret input is that only the prover, meaning that the person who executes that, needs to know this witness input, but the verifier doesn't need to know what it is, and that helps us to do private stuff, which is really nice. So, and in the context of a blockchain, we can even do this one step further. Instead of like a initial input, we just call this initial input initial state commitment. Like it is a hash of a state, or like a commitment that we just provide the real data in our secret input, and we get a final state commitment out. And then for the verifier, it just looks like the change of a commitment, but we are still sure that everything was correct because the proof is verifiable. So yeah, that's basically it. So why do we need ZK-VMs? And basically, it's way easier to use. Like, we don't need to learn cryptography, we don't need to code circuits or whatever the people are doing or were doing like 2 years ago. So basically, now we can build in Rust or in any other language real programs that we get a proof of execution after it. It is universal, so a Turing-complete zero-knowledge virtual machine can execute any program and we get a proof out of it. And it also is way simpler than doing circuits, so we can basically have, with a relatively small set of constraints, we can describe the whole virtual machine, and it's built for recursion, or like recursion is way easier in a virtual machine context than if you would use circuits. So basically, the bad thing about ZK-VMs is that it doesn't work with all proving systems, but this, like for Starks, it works pretty well, and the performance is worse than if you have specialized circuits, but you can have specialized circuits even within the VM to even it out, but it will always be slower than when you would go for a pure circuit approach for a single program, for example. But yeah, these are the trade-offs. And so if you decide to build a ZK-VM because you want to have this because you want to have this ease of use, then basically you can decide how you build it and which instruction set you target. And even if you're not technical, you might have heard that, for example, there's RISC-0, and they target the RISC-V architecture, which is a well-known architecture, and then it's easier for people to use it. You can also target the EVM, and this is what the ZK EVMs are doing, right? So they try to prove EVM bytecode, and so this could be the target of your virtual machine, of your zero-knowledge virtual machine, or you can have a new instruction set that is optimized for the zero-knowledge stuff. like the EVM is not really optimized for zero knowledge, but you can build a whole new system or instruction set is optimized for that. And the pros and cons of that is like basically for the mainstream way, there's lots of tooling, lots of expertise. Like when you have the whole Rust community building tools, then you can plug into that. It's super cool. For EVM zero knowledge virtual machines, you have some expertise and some tooling, at least everything that is already there in Solidity. For a new instruction set, there's no tooling. And so you have to build everything from scratch. But you can build it very blockchain focused. This is our goal. So basically, you can optimize it for a certain use case, and it is then in this use case more performant. Right? So EVM, to prove EVM code probably is not so performant, or you need way bigger machines than with a specialized virtual machine that is built for this kind of performance. The Miden VM itself, it basically is a Turing-complete, stack-based, optimized virtual machine, and it is built for client-side proofs. That's why we want to optimize it. Basically, we want that people on their mobile phone can create a proof and send it to the blockchain. This is the goal, right? And because this solves a lot of problems in the blockchain world, as we think. And the second goal is it is efficient for blockchain. So for like stuff like hashing or Merkle path inclusion proofs should be very quick. Whereas we don't need to run Doom on our virtual machine. For example, like these could be trade-offs. And it's like on a high level, it is a stack-based virtual machine, meaning that we have a stack. You can add new elements to the stack and remove elements. We have a read-write memory for the programs, and we have like specialized chiplets to optimize execution of certain operations. For example, for hashing, we use our own hash function that's optimized for this environment and our prime field. But like there are several other chiplets, like our kernel chiplet, for example, that holds all the procedures that you need to touch very often, or that you can load a certain kernel with this virtual machine. And it has a host interface, and this is how we manage the secret input, like with an advice provider, where we can add or inject data to the virtual machine that the verifier doesn't need to know at the end. But this is where we inject basically all the data, like the real programs and the real account states, and like the lion's share of the data gets provided during the advice provider, and the initial stack or the initial input of the VM only holds commitments to this data that we inject as secret inputs. And as for the chiplets, so what are we doing? What did we need to optimize? Basically, it's range checking. So in the VM, we oftentimes need to check if a certain number is in a certain range. These hashes, as we said, that we want to optimize for blockchain use cases. So we need to have optimized Merkle path and this 2-to-1 hash, like when we want to merge something. We have bitwise operations that we outsource to a chiplet, and our kernel procedures. And like, I don't know how deep you're into, but whenever you have starts, then you have an execution trace, and this could be actually interesting. This is how the VM works. Basically, there's a huge matrix being built. Like this is how it looks like when there's a program being executed, and it's just like a huge table, and every row in the table is one state of the VM. And then whenever we switch to the row, we need to uphold certain conditions that we can express in polynomial constraints, and meaning that a program execution looks like we go row by row, state by state by the VM, and there are certain information in certain columns, and at the end we can just add all these polynomial constraints, and then we have a huge polynomial that we can commit to. But this is basically an execution trace. This is how ours look like. We have we have the program decoder, which basically is responsible for executing the program that we inject into the VM, right? So out of this the numbers that we give it via the device provider, it decodes it again into instructions for program, and it is responsible for hashing this program at the end again, such that we get always the same program hash regardless of which part of the program we're executing. It has an operand stack. This is our main processor where we manage the stack, right? So basically, what I said, we have this stack, and then you can add elements or remove elements, and this is being handled in the main processor. And then we have the chiplets that I was talking to, where we want to where we can do optimize computations. Our programs at the moment, they look like this. This is like one of the trade-offs I mentioned before. At the moment, we don't have a Rust compiler. In the future, hopefully we have it. But at the moment, our programs, they look like an assembly-like language, basically, and they get compiled into something that we call a Merkleized abstract syntax tree. So basically, our programs can be expressed as a Merkle tree, and I will explain later. And these Merkle trees or syntax trees, they get executed in the VM. And why are we doing this abstract syntax tree thing? Is basically what it is that all programs can be reduced to a single hash, which is a super nice property in the blockchain context. So if someone claims to or wants me to execute a certain program, then I can always quickly check the hash, and I know it's exactly the program that I knew before or that I already have executed. There is no change in the program and no loophole or backdoor that someone coded in. All the nodes of this tree, they are programs itself, which is also super nice. So that helps me to execute only parts of the program, and I don't need to unhash the whole program if only very limited parts of the loop or so are being touched. This makes it efficient, and like the bottom of the tree or the leaves of the tree, they are just linear programs that I just execute them. But as an example, it looks like this is how the assembly code looks like, and then it would be translated in something like that. So where on every node, again, the program decoder can put that in the VM into a program regarding to the inputs, whatever inputs it has. Why do we want to have these Merkleized trees? As I said, it's way more efficient. So we need to hash only the code that we really want to execute. This saves us gas, but also it's just for clients approving. It is way safer, so we know the hash of the program, and then we always know which program we are going to execute, and it also helps us with privacy, with having private programs that only have these post and preconditions. I don't even need to know the program at the end as a verifier if I know the hash of the program. And so we want to have a fast VM. How fast is it? This thing was being built by CKbench, by Polybase, a full team. They put it together. It's some month old, but here you can see Risk Zero, Noir, Leo, and Miden. And the big thing is the Fibonacci. So basically, their Miden is quite fast, almost as fast as Noir, which is circuit-based. You can see, and for the blockchain stuff, which is down there, the member inclusion proof and the merge, we are really fast, but there are these downsides that we need to code in assembly because of that, and we have our own hash function. On the other hand, Risk Zero, for example, is just for a different use case, or slightly different use case. They are easier to use and more universal. They can run Doom on their VM now, as they have said yesterday, which is super impressive. On mine, you cannot run Doom yet. Exactly, but there you can see the different, basically, trade-offs. So, as I said, let's try to create a zero-knowledge proof together. I don't know if you've ever done it, but you can just scan this QR code with your mobile phone. And if you want to try it, maybe you can come up with the homepage, So now, when we see the homepage, basically it runs on your mobile phone, the Miden VM, in the browser. So we can compile it to Vasen and can run it in the browser. And when you click proof, it should be in a matter of milliseconds, hopefully, that it proves the small program that you can see here. Yeah, like this is very small, but it's just a program that adds 1 and 2 together. So we expect 3 as a result. And when you can click proof there, can you maybe click on this super tiny button there? Then. So never do a live demo. Yeah. Okay, so basically here you can see the program hash. It's a super small program, only 64 cycles. This is the proof, and you can click here maybe on verify, this huge monitor, and then you can see. And your mobile phone should be quicker, but yeah, 16 milliseconds. Yeah, and then basically this is the Miden VM running in your browser. For the blockchain use case, the programs are obviously bigger, but our goal is when we hit mainnet, end of the year, beginning of next year, that they prove on a MacBook only takes 1 to 2 seconds. And yeah, this is all powered by the Miden VM then. The Miden rollup is a bit different, but just long story short, our goal is that people can create client-side proofs to prove their state transition to the blockchain. And this solves many problems that the blockchain suffer today. But to be able to do that, you need an efficient, blockchain-optimized, zero-knowledge virtual machine. And this is Miden, basically. You can play around on this playground and code a little bit in Miden assembly if you want, and prove these things. Yeah, happy to hear your feedback, and thanks.